I'm excited to be here to share our work on digital twins in additive manufacturing. And the topics I have planned are shown here in yellow. I will start with the basic definition of what I mean by additive manufacturing, because there are many different types of additive manufacturing, and what I mean by digital twins, so basic concepts, and then the type of fundamental problems that are generic to additive manufacturing and how we solve them using digital twins. Define a little bit about the components of digital twins, how it works, mechanistic models and database models, control models, and data itself, and then how they are used in industry and what is in store in the future based on evidence. What is so special? GE fuel nozzle is a component that is often cited as an example of the unique capabilities of additive manufacturing. This is made layer upon layer in thousands of layers, but previously it required assembly of 21 parts. It has increased the reliability of jet engines according to GE. We can make materials that are compositionally graded. This is a big deal in the nuclear industry, where we have many dissimilar alloy joints, particularly welded joints. And these dissimilar alloy welded joints often fail because of high temperature degradation of property that we call creep degradation. Particularly carbon diffusion is very often one of the difficulties. And by using a graded joint, we avoid the dissimilar alloy joints, and the properties of this joint is so much better that the component life can be extended by a very significant amount. Also, this same additive manufacturing machine can make numerous different parts. And one example is the production of a ratchet wrench inside the space station. They needed a wrench, but there was no resupply missions planned. So NASA remotely printed a plastic wrench in 104 layers within the space station by just sending remotely a computer code. So there are many unique capabilities that make additive manufacturing a very desirable addition to our tools of making materials. I'm going to focus on metal additive manufacturing. So there are many different techniques, but in particular, I'm going to focus on three specific ones. One is called powder bed fusion, where we have very thin layers of powder. Layers like 20 to 50 micrometer is typical, and powders are of small size, maybe 20 to 30 micrometer in diameter. And after one layer of powder is laid on the bed, we pass a laser beam, traverse it based on a computer program, and melt and deposit a layer of metal. And we keep repeating this thousands of times until a 3D component is made. In this case, I am showing a statue of a lion, which is the mascot for our football team. So numerous different parts of intricacy can be made using this powder bed fusion laser process. Again, the final finished product has a very good surface finish, and we can make parts as big as about 80 centimeter by 40 centimeter by 50 centimeter using a laser beam. We also have another technique that we call directed energy deposition using a laser beam. Here the powders are fed coaxial with the laser beam, and a computer guides the passage of this beam and the interaction between this beam and the material. Particularly, it melts the powder while it is being deposited, as well as on the part itself. And eventually, we do many layers of deposition, very thin layers, sometimes thinner than a human hair, and we make a 3D part. When we need to make a very large component, these two laser-based systems take a long time to make because we are making very thin layers. So there is another technique that we call directed energy deposition gas metal arc process. In short, DDGMA, or GMA stands for gas metal arc. And here we can make large components very quickly because we have a consumable wire electrode that we melt using an electric arc. So the deposition rate is much higher than that for the powder bed fusion or directed energy deposition laser system. And the only drawback here is that the surface is not very smooth. It has waviness and roughness, but it can make very large specimens very quickly. These are the three main processes that I'm going to be focusing on for metal additive manufacturing. Now, what is a digital twin? In short, it's a virtual copy of the process. But this particular definition doesn't begin to tell what exactly this is. It contains many tools of the virtual world, and it interacts with the physical world in real time using the internet. So it can check the health of the machinery, it can check the attributes of the product that is being made, it can avoid defects. How does it do that? It does that by using different types of models. Physics-based models, data-based models such as machine learning and statistical models, and overall, the performance of this virtual replica of the physical process improves with time because this particular tool also gets data and it uses data. So more data means we can do better in terms of the quality of the parts that we make. How does it do that? There is a sensing and control system in place. So based on the past performance, we can control the process variables in order to get better quality of the parts. And sometimes we can even expedite the formation of a given part. So it can minimize the number of trial and error tests to improve quality and reduce defects. So it can also expedite part qualification, and it can reduce cost because we are not throwing away specimens. The quality consistency improves, and specific components depend on the purpose. So there are a lot of things here: machine learning, mechanistic models, statistical models, control models, big data, there is sensing and control, and process variable control, all of these. So although the digital twin per se is a tool of the virtual world, it does not operate in vacuum. It must have a hardware for it to control the hardware. Of course, we can run the digital twin offline to plan for a process so that our process is sound and the parts we make are as good as we can make. And this is without any trial and error. This is all based on scientific principles. So what is a mechanistic model? By mechanistic model, I mean physics-based models that can tell us the effects of variables that are called input variables and effects of properties of the material that we are depositing. So thermophysical properties, for example. This model is a static model. It does not change with time. After it has been tested and validated, it is not connected to the production necessarily. It does not have to be connected via internet to a real unit for it to function. And it does not need any sensor. So this is a self-contained physics-based model. Sometimes the physics is very complicated, particularly in a relatively new technology like the additive manufacturing. So there we have data, and we can use the data in machine learning as well as in statistical models. So these are data-based models that can be run anywhere for various input parameters. These can be dynamic. That means if we get more data from the sensing units, the larger volume of data will improve predictions, and therefore the quality of the machine learning output and the quality of the statistical model guidance will be more appropriate, more correct. It may be connected to production, but does not have to be. And sensor data may be provided as inputs to the model. So you see, this is kind of dynamic. With time, the quality of prediction will improve. So digital twin, here is an example. This is a physical asset, an engine. The data is fed by various sources. Here, the digital twin is connected to the physical asset via internet. It's connected to production, maintenance, testing, and even part performance. How does it do that? Based on past experience and based on models. So it is internet-based, uses mechanistic models, machine learning, statistical models, and data. So the digital twin will be connected to the physical twin or physical asset via the internet. That's the interrelation between mechanistic model, database models, and digital twins. The digital twins will have all of these and more depending on the specific use. So what's the basic problem that we are solving? We have said that additive manufacturing is a relatively new process. So let's look at some of the characters from the data that have been reported in the literature. So we have a laser beam or an electron beam or an electric arc as a heat source. So power is an important parameter. Similarly, the heat source and the material, there is a relative velocity that we call scanning speed. Scanning speed can vary by about 1,000 times. Power can vary equally about 100 times. And when the material experiences this variation of power and speed, the cooling rate that determines the scale of the microstructure also varies very significantly from about 100 degree Kelvin per second to well over 1,000,000 degree Kelvin per second. And heat input, which is the ratio of power to speed, so this is a measure of the amount of heat deposited per unit length of the specimen, that also varies 10,000 times. The main point is there is a huge diversity of process parameters that makes optimization of structure and properties by trial and error method very slow and very expensive. It's expensive because the equipment are expensive and the feedstock material, the powders of that small size, is much more expensive than sheets or wares or other common materials that we encounter every day. So this is a fundamental problem, a very large process parameter window from which we have to select a set of process variables that would give us the optimum quality of the parts. The growth rate, solidification growth rate, the temperature gradient, they also vary very significantly. And these two parameters control the morphology of the solidification structure, whether they are equiaxed or columnar. So that also, there is a huge variation of temperature gradient and growth rate. And if you plot the heat input versus properties, it is no surprise because the cooling rates are different, because the temperature gradients are different, because the growth rates are different, the scale of the microstructure, the kinetics of different phase transformations, and the solidification morphology all are at play. And we have to be very careful in selecting our process variables so that we get the optimum values of part attributes. And this is not a trivial task, particularly if we do it by trial and error process. So the challenges we face can be divided into three categories: scientific challenge, technological challenge, and economic challenges. So I'm going to show you some of the challenges in each category. Process structure, property, performance relationship is what we do in material science. And the goal is to control the microstructure, defect formation, control the morphology of the solidification structure and grain structure. All of these are at play. So these are some of the scientific issues that we have to deal with. In terms of technological issues, part qualification is a big deal. It's a big deal because if the parts are not certified, then we have to redo our parts, and that is very expensive. We can make very complex things using additive manufacturing, but there are limitations of complexities. There are geometric limitations of what we may be able to do easily and what is very difficult to do. And then scaling up. Let's say that I do a small part. It doesn't mean that I can do a large part that has some intricate things. We need support structure design in order to make very intricate parts, such as a part with cooling channels embedded, or a part that has small and large features included in the part. Process design and sequence. I'm going to show you some examples of that later on, that we worked collaboratively with University of Michigan. And then post-processing is important. Remember, I said that some of the surfaces are rough surfaces, and those are areas where cracks can be nucleated depending on the triaxial stress state. So some of the printed parts have to be finished using standard tools of surface finish. That adds to another technological challenge. Also, we sometimes have support structure for intricate parts. They have to be removed. And removal of this support structure adds cost and creates a technological problem sometimes. Economic challenges, we have relatively lower cost conventional manufacturing with which we sometimes compare 3D printing, at least where a part can be made by both processes. Although 3D printing can do many things that conventional manufacturing cannot do, some of which I have shown. So there is no standard. That's another difficulty. And because there is no standard, sometimes it's difficult to know what we are shooting for. So that is also a commercial problem because we don't know whether an agency like Federal Aviation will accept our part. Feedstock compatibility is a problem. Not all metals and alloys are available in powder form or wire form. So that is a difficulty. And because it is a newer technique, intellectual property and experience and training of people are also an important economic challenge. One of the ways of reducing uncertainty is to use scientific principles of physics that we call mechanistic modeling. It correlates the input, which is very often process variables and thermophysical properties, and attributes of the part as output. What are the attributes that we are concerned about? Microstructure properties in general, but a lot of other things. They will become clear as we make progress in this presentation. But we are relating input with output based on laws of physics. So what's the requirement for being able to do that? We need to know the mechanisms of action. Otherwise, we cannot apply the laws. So capabilities of mechanistic models. So let's say that we have developed a mechanistic model. We provide the process variables and thermophysical properties of the alloy as input. And what do we get as output? Transient three-dimensional temperature fields, cooling rates, temperature gradients, solidification growth rates, all of those parameters, right? As a function of time and position within the part. We also get some idea about the defects because these models can compute the geometry of the fusion zone. And there has to be significant overlap in nearby tracks and nearby layers. So there cannot be an open space because if there is an open space, there will be lack of fusion voids. Also, the heating and cooling based on the component property can result in residual stress and distortion of the part. So that is also something that can be modeled based on physics and mechanics. Microstructure models are being developed. So that also can be predicted based on transient three-dimensional temperature fields and other parameters that we calculate from mechanistic models. And grain structure and morphology can be computed. We often start with heat transfer and fluid flow calculations. Heat transfer and fluid flow calculations is a requirement for understanding time, temperature, excursions at various locations within the part. Thermal cycles is what we call it. It can also take into account the properties, thermophysical properties of materials. So the role of alloy and AM process variables can be evaluated using a heat transfer and fluid flow model. We can determine the geometry, composition, and structure. We already know the composition of the feedstock. Why do we need to worry about the composition anymore? For various reasons. Composition is not homogeneous. The material that we deposit is inhomogeneous in various scales. A simple example. Let's say I'm depositing a 6000 series aluminum alloy that contain volatile components like magnesium. Aluminum and magnesium have different volatility. So selectively, magnesium would be vaporized. So the composition of the part can be different from the composition of the feedstock material. So we have to worry about not just the structure and geometry, composition as well. We have to worry about different types of defect. Spatial and temporal variation of cooling rates can give us variations of property and microstructure. So microstructure and mechanical properties, if we want to understand, we need heat transfer and fluid flow model. Residual stress and distortion, temperature field is a required input to such models. So if we want to minimize the trial and error testing, we need heat transfer and fluid flow model, composition change, grain size, topological features, and finally, printability. Printability, all alloys are not equally printable. Some alloys are easy to print, others are not able to resist distortion, lack of fusion, composition change, and so on. Blue, we have pretty good models. The ones that are in the red, there are some models, but they are still being developed. So what does it provide? Let's say that I have a monitoring location and I'm building this wall using additive manufacturing. So I put a thermocouple here and I measure temperature versus time plots. See the type of peak and valley that we get in this. So that is the thermal excursion that one can predict using these mechanistic models. So what type of model are these? They are basically Navier-Stokes equation solver and Fourier second law solver, numerically computed, and calculations are pretty reliable for calculating the thermal cycles for different process conditions. It also calculates the fluid velocity. So these are streamlines. Liquid flows from the middle to the periphery because of spatial gradient of interfacial tension, which is a stress. And this stress is known as Marangoni stress. Because of this Marangoni flow, we have mixing of the liquid within the fusion zone, and that determines the temperature field, the temperature gradients, the cooling rates, and all kinds of other parameters. The fusion zone geometry is not always hemispherical. It depends on two parameters. One we call Prandtl number, which is the ratio of momentum diffusivity to heat diffusivity, and Marangoni number, which is a measure of the strength of the Marangoni flow, velocity. Large velocities would be large Marangoni numbers. So depending on Prandtl number and Marangoni number, we can have a hemispherical pool, or we can have a pool that is of the shape like W, or like a bracket. Also, composition is very important. If we have a small amount of what we call surface active element, such as oxygen, sulfur, selenium, tellurium in steel, they change the temperature gradient of interfacial tension, which is a physical property. And depending on that property, we can have a flow going from the middle to the periphery, or we can have a flow that is going from the middle downward. So it will act as a thermal drill, because right in the middle of the pool, the temperature is much higher than at the periphery. So if we have hot packets of fluid coming down, we will have a deeper pool and a narrower pool. If we have fluid going sideways, we will have a shallow pool and a wide pool. If we compare the three additive manufacturing processes, the powder bed fusion laser, directed energy deposition laser, and directed energy deposition with gas metal arc power source, the size and shape of the fusion zone is going to be different. The scales of these are very different. Like this length is about 8.4 millimeter here, whereas this length is only 0.6 millimeter. So there is a variation of tenfold in terms of length scale. Also, the morphology are different. Here, we are depositing powder. Here, the arc is depressing the liquid. And in powder bed fusion, this is a very tiny, teeny pool, 0.3 millimeter in length. So this may be 50 to 100 micrometers. The size is different, the temperature fields are different, and everything else like cooling rates and geometry will also be different. Power and speed are also very important. If we have a higher laser power, that means we are depositing more energy per unit time. And what that means is that there will be a bigger pool, so the pool will cool slower, so it will take more time, so the structure would be coarser. If we take a stainless steel 316 and measure the secondary dendrite arm spacings, they will be somewhat larger than if we were to use a smaller laser power. Simply because lower power means faster cooling, so the coarsening will not be as pronounced as in 2.5 kilowatt power. Similarly, if we take an aluminum alloy and look at the morphology, how the grains change, the grains would be mostly columnar grains, except right in the middle. And I'm going to show you this more closely in the next slide. But the morphology depends on temperature gradient and solidification growth rate. These are the most important parameters. The cooling rate determines the scale of the microstructure, but not the morphology. This is the fusion zone. When this moves, this is the growth rate. This V is showing the scanning velocity. And right here, we are showing equiax grain. Right here, we are showing columnar grain. The solidification morphology depends on the ratio of temperature gradient to solidification growth rate. And this we have computed from a model. And this one shows G by R. G by R is temperature gradient by growth rate. And this is the morphology parameter. It's varying from 0 to 40 here in this scale. And you can see right in the middle, we have a low value of G by R. G by R is this ratio. So we are getting equiaxed grains in the middle. And outside of this region, we have columnar grains because of the high values of G by R. And that is what the model can predict. So models of grain growth can pretty much tell us what to anticipate in terms of the morphology of solidification. I want to show you some research we published 7 years ago in collaboration with Professor Muzumdar of this department. Late Professor Muzumdar, I must sadly say. But what I'm showing you is unidirectional scanning from left to right always. And what you get is a fusion zone like this. Solidification occurs as we move this liquid along, and the heat flow direction is perpendicular to the fusion line. So here the heat flow direction would be where my cursor is showing, and this is the heat flow direction. So for a simple cubic material like Inconel 718, they will grow along this direction. And this is what we actually see when we do the experiment. These experiments were done in mechanical engineering department here. We did the simulations. Now we want to change the rules. We want the laser to go from left to right and then backwards, from right to left and then left to right. And we will call this bidirectional scanning. So we have a polycrystalline substrate, 718, and the heat flow direction would be different, right? because when we are going from left to right, the fusion zone looks like this one. The isotherms are compressed ahead of the beam. Here is the beam, and expanded behind the beam. Whereas it is going on the right to left, the fusion zone is somewhat like this here. So here the main heat flow direction is perpendicular about 60-degree angle here, whereas here it's at this angle. So they are different. So I'm going to show you that. So what happens, these are the directions of heat flow now. And look at the orientation of the crystals. They change in a zigzag manner, just like we would have expected from simple heat transport. Starting with a heat transfer and fluid flow model, we can do a lot of things that are otherwise difficult to do. Distortion and residual stress are important factors. And what we do here, we start with a transient heat transfer fluid flow model. We do the temperature calculations, and we feed this into Abacus through a Python script, and we get the residual stress and distortion calculations done using very accurate transient three-dimensional temperature fields. And we can calculate the relative values of residual stresses for directed energy deposition gas metal arc, directed energy deposition laser, or powder bed fusion laser. Powder bed fusion laser has the smallest size of the fusion zone, and the residual stresses are the lowest, whereas gas metal arc directed energy deposition, the residual stresses are larger. Also, we can check the relative values of residual stresses for different materials under different conditions. So those are some of the benefits of doing these models. Not everything can be done by mechanistic model because of the lack of mechanistic understanding. There we use data-driven relations, either based on machine learning or statistical modeling. So I'm going to give you an example. The problem with an Abacus model of residual stress is that it takes a long time to do these calculations. Whereas if we can take the data from the Abacus model and make a neural network, we can get maximum values of the tensile longitudinal stress, which is very often a big problem in additive manufacturing. And we can generate a neural network so that after the neural network has been validated and adequately tested, we can use the neural network to get mean values of maximum longitudinal residual stress and other parameters. We can also figure out which parameters are more important and which parameters are less important for developing residual stress. Feature importance, if you will. For example, here we are showing that preheat temperature is very influential in controlling the residual stress. So if we want to lower the residual stress, we need a preheat. So higher preheat temperature is beneficial. And then there are other variables like yield stress at room temperature is important, but not as important as the preheat temperature. So these are some of the benefits that we can run. Defects are a big problem in additive manufacturing, particularly cracking. What are the important variables? Laser power, laser beam radius, scanning speed. There are a whole host of variables. I'm not going to read all of these, but I promise you, if you count all of these, you will get 12 important variables that can affect the cracking. So if I wanted to do experiments by trial and error to avoid cracking, I will need to do, if I did a two-factor design of experiments, DOE in short, two-factor design of experiments will mandate 4,096 experiments. But if I look at the non-dimensional numbers, I can bring these 12 variables down to only 4. So we'll need 16 experiments only instead of 4,100 experiments. How so? Think of the flow of a fluid through a pipe of circular cross sections. If you wanted to know the structure of the flow, laminar or turbulent, you will need to know the diameter of the pipe, you will need to know the velocity of the fluid, you will need to know the density and the viscosity. So how many variables? 4 variables. But someone who has studied fluid mechanics will say, I don't need 4 variables. I can use just Reynolds number. If Reynolds number is higher than 2,100, the structure of the flow is going to be turbulent. If the Reynolds number is 5, it's going to be laminar flow. So it is like this here. If you know physics, you can mix physics with data-based models. This is an example. How so? If we take these 4 variables, solidification stress, ratio of vulnerable to relaxation time, temperature gradient to solidification growth rate ratio, and cooling rate, we can do a regression analysis to form a cracking susceptibility index. And a higher cracking susceptibility index is bad news. A lower value is safe. No cracks are observed. Again, we can do feature importance. The solidification stress, sigma, is the most important variable, followed by the other 3, vulnerable time to relaxation time ratio, the temperature gradient to growth rate, and cooling rate. So we can do a lot with data-based models. Rough surfaces are a problem because they lower the fatigue life, they give lower dimensional accuracy, and in extreme cases, it results in part rejection. So what can we do? We take all the variables, we take their dimensions, and we do a simple Buckingham Pi theorem and find out, based on our data, we take all the data and we take the correlation based on Buckingham Pi theorem, and we can do rapid screening of a whole lot of experimental data using dimensionless correlations very, very quickly. And thereby we can get conditions for smooth printing of parts, metallic parts, using correlations that are obtained by data-based models. Feature importance can also be determined, like heat input is the most important variable and contact angle is not so important for surface roughness. So we understand that these are some of the components of a digital twin. So tools of the virtual world and physical worlds, they have to work together. So what are some of the examples? How do we make use of the digital twin in real time? Mitigation of defects, for example. We have a thermo camera. Here is the data. So if we plot it, this is how the solid dust temperature looks like. From here, if we plot the angle versus distance, this is what this would be. And we can do a classification problem using support vector machine or some other common tools of machine learning that are available freely. We can separate the cracked parts from the conditions where no cracks would be observed. So how do we actually implement this? One of the ways is to have a sensor, thermal imaging sensor, or a strain gauge to measure the distortion. And this sensing data will be fed to a control model, and control model will change the process variables in order to get a structurally sound and reliable part. So the benefits are many. First benefit is that you remember I said that the parameter space is very large. Cooling rate had a very large range. The temperature gradient had a very large range. So one of the things of virtual testing using digital twin is to reduce this parameter space. And therefore, the physical printing is likely to result in sound parts. So that is one of the benefits of using a virtual testing using digital twins. We are talking about mechanistic modeling, machine learning, and digital twins. And if you look at all these steps like product design, process planning, production, monitoring and control, defects, microstructure properties, inspection performance, machine learning can do all of those steps. Digital twins are very helpful in controlling so many of the attributes, and so are mechanistic modeling. So all these can work together to give us a better product. Currently, they are widely used in industry. General Electric uses more than 500,000 digital twins. NASA and US Air Force uses digital twins to increase reliability and safety of vehicle designs. Fraunhofer uses in 3D printing, and so does Siemens. So the digital twins are here to stay. They are being widely used in industry. And we still can improve the digital twins if we have more data. For example, printability data, microstructure property data that are alloy specific. So these, we have to be patient. Sharing of data for machine learning. Digital twins are also goal specific. If we look at the sales data for equipments, the outlook is pretty good. And using digital twins, we can improve quality without trial and error. We can select the right alloys for a part, and we can do our qualification very quickly. And all these things will lead to market expansion. Thank you.